Okay, so we have this question right here. It says an actor is wearing a harness. The harness is connected to a cable and support as shown. The force on the cable must not cause the material of the cable to reach its yield point. State what is meant by the yield point of the material. It's simple, it's a book definition. Yield point is something like it is a point where if the force is increased, it will go under a sudden or a large deformation, plastic deformation. Okay, so it's a book definition, just simple, right? That the stress value, even you can write strain value, any of those value, when it reaches stress value at which a material undergoes a sudden or large deformation. It's like nothing new, like it is nothing much to explain. Is that if you have seen a spring, right? If you just like stretch it out a lot, it will reach to a point where it won't go back to its original shape. It will be much more extended. That's basically yield point, right? Where the sudden basically deformation starts and it won't go back to its original shape or form. Okay, so we have this question right here. The cable and harness are used to accelerate the actor vertically off the ground. Explain why the forces acting on the actor cause him to accelerate upwards. It's like very simple thing. Like how can an actor could go basically up, right? When basically this is your actor right here, okay? So this is the actor's weight and this is the cable him provided, right? If the tension value, if the upwards force value, in other words, the tension value is greater than the weight value, then if he will go up, the resultant force will be upwards, right? So it's simple as that. You need to explain that so that the force, in other words, is also called as tension, is in the cable. Make sure to mention that the force in the cable, you can't just simply say force, the force in the cable is greater than the weight of the actor, so the resultant force will be upwards. Okay, properly upwards. Okay, so yeah, this is your answer. Okay, so we have this next part right here. It says the actor has a mass of 77 kg and is lifted vertically from the ground with an acceleration of 2.1 meter per second square, and you need to find the tension of the cable. Okay, so it's a very simple question, but you need to do it step by step. Without steps, without strategy, you can't solve this question. Okay, first step, identify the values you have been given. Okay, so if you identify the values you have been given, so you have mass and acceleration, right? And you need to find the force, or basically in other words the tension, right? You need to find tension. So most of you, I know what you guys will do is that you will directly do F is equals to ma and then put mass and acceleration and blah blah blah, and we'll know that, oh well, it doesn't match. What is happening here? It is because you don't know the Newton's second law properly, because this formula is Newton's second law and you don't know that properly, right? So let me explain you Newton's second law properly. Okay, Newton's second law says that net force is the product of mass and acceleration. He did not say that force is the product of mass and acceleration. He said net force is the product of mass and acceleration. So how we will write it? We will write it like this. This is your net force, right? So we do have mass and we have acceleration. Do we have included all of the forces in the net force category? No, we did not include everything. We just said that this is only tension. We only have tension. Where's the weight? You forgot about the weight, right? So let me draw this. This is the actor. We have weight acting downwards, and then we have tension acting upwards, right? So now you can take any motion of direction, positive, right? Up positive or down positive. I will take down as positive. So if you take down as positive, your tension will be negative. So it is written as W minus T. This is your net force and MA. So you don't have W. You can find W from multiplying mass with gravity. W is equals to mg. So if you do 77 times 9.81 minus tension equals to the 77 times 2.1. Okay. Now if you solve this whole values, you will get your answer as, I have the rounded off value with me, so it's 917 Newton. Okay. Okay, so we have this next part right here. It says to make sure the actor is safe, the stress in the cable must be less than 15% of the yield point stress. The cable has a yield point stress of this. The diameter of the cable is given. Tell me whether it's safe if we move the actor with this much acceleration. So first step, identify what values you have. Okay, what values you have. Okay, now I have basically I have the limit, I have diameter, and I need to find the stress. So right off the bat, let's eliminate the first point here. So let's figure out the limit we have. So it's 15%, which is in other words 0.15 times 2.5 times 10 raised to power 8 pascals. So if you solve this, you will get your answer as 3.75 times 10 raised to power 7 pascals. Okay, this is the limit. Okay, we can't exceed this limit, otherwise it's not safe for the actor to use the cable. So let's find the limit now. So stress, we need to find stress. Stress formula is F by A, right? And we do not have A, so we can use this formula to find A, which is pi r square. Why pi r square? Because our wire is having a circular shape and this is area of circle, so that's why we use pi r square. So let's input the values. R, in order to find R, you can do it diameter divided by 2 because we have diameter. So 7.6 times 10 raised to power minus 3 divided by 2 and square, and then put this in area. Here you have force from the previous part, which is 917. Area 7 pi times 7, wait, let me go a bit more down, 7.6 times 10 raised to power minus 3 divided by 2 square. Now if you solve this, you will get your answer as 2.02 times 10 raised to power 7 pascals. Okay, so now you can see that this value is less than this value, so it's safe for the actor to move across with this much acceleration. Or how much acceleration was it? 2.1 acceleration. Okay, you just simply say that 2.02 times 10 to the power 7 pascals is less than 3.75 times 10 to the power 7 pascals, so it is safe. Simple as that, right? Faster, right? Okay, so we have this next and last part right here. It says the original cable is replaced with new cable made from different wire, right? Highlight all the important points. Cable is replaced with new cable, different material. This material has lower Young modulus than the material used to make the original cable. Okay. The new cable has same length as the original cable but has a greater diameter. The breaking stress is same for both cable. Explain how the work done to break this new cable is different from the work done to break the original cable, assuming both material obey the Hooke's law up to the breaking point. It's very simple. Okay, let's do it step by step. Okay, so let's first write the formula to understand it, right? So first step, write formula. So what is the formula? The formula is Young modulus equals to stress by strain. Okay, so we're just talking about the new material, right? This just the only new material. So he says that they say basically they say that the young modulus is less, right? So now the young modulus is less. Now the first thing that comes in my mind, right, without reading any further, just the young modulus is less, is that either the stress has to be same and strain has to be greater, or stress has to be less or strain has to be greater, or just the stress has to be less and strain doesn't change at all. Okay, this way the young modulus will stay less at all times. Okay, so this statement come in my mind, right? This thing just instantly come in my mind. Okay, second step, now this said that the stress is same. Okay, the breaking stress is same, so we eliminate this point here, this point here, this point here, this point here, means that the strain is greater, and we reach to a conclusion that strain is in this case is greater and stress is same, right? In that case only the young modulus can be less. Okay, simple, right? Now we have to explain it. We can't just say, oh well, because of the formula, because we have to mention this in 4 marks, right? How we will mention it properly. So let's dive into the stress and strains formula, right? Stress, now stress is F by A. So they said that the diameter is greater, right? And the, let's say, did they say anything else? Diameter is greater, breaking stress is same. Okay. So if diameter is greater and they want to keep the stress same for both cables, that means the force has to be greater in order to match, in order for this stress to be matched up. Okay, because if you only increase area, then the stress will be less. If you only increase force, then the stress will be greater, right? Just I'm explaining that you have to make both values to be equal, otherwise the stress will have a varying values. It will be not same as the other cable, the old cable, the original cable. Okay, so we have came to a conclusion that if the diameter is greater, area is greater, then force is greater. Okay, force needs to be greater, it's required that we need a greater force to make it, sorry, to make the stress not be changed. Okay, now third step, let's go for strain. Okay, so how this strain value is greater? So it says that it has the same length, right? We know the formula of strain, which is extension by original length. So original length is same, but if original length is same and the strain value is greater, then the extension has to be greater. Okay, simple as that, right? If strain is greater, extension has to be greater if the length of the cable is same. Okay, for both of the cables length are same. Okay, original and the new one. Okay, so from these I got to know that the if the a diameter is greater, area is greater, then the force is greater. If force is greater, then and for the strain part, if the original length is same, then the extension has to be greater. Okay, simple. Now, if these both things are greater, do you remember the formula of elastic strain energy, right? Basically, you know that work done is energy. Okay, so elastic strain energy is has a formula of 1 by 2 F delta X. Now they are both increasing. So energy will increase. Energy increase, work done increase. Means you need more work done to break this new cable, right? That's how it is different from the original cable. Okay. So we have to explain all of this in a very simple way. Okay. So first thing we will mention is that about the stress thing. Okay, what about the stress thing? That the new cable has a greater basically cross-sectional area. We always say them cross-sectional area, not only area, cross-sectional area. So if it has a greater cross-sectional area, then it means it means the force is required to be greater. Is required to be greater. Okay. First thing out of the way. Okay. And we also have to give the reason. We only just stated something, but we didn't give the reason. What is the reason? Oh, how I can say that this point that I have mentioned is valid? Because I need to give the reasoning as well. Because new cable has low young modulus and there will be greater, oh yeah, this is, sorry, next point, there will be greater strain, right? Why? Because the young modulus is low, right? So as we have discussed the third point, there will be greater strain. And how so? How the strain will be greater? We have to mention that the original, the length is same for both cable, so the extension has to be greater in order for strain to be greater. Okay. Now we have given our three statements here. Now the final thing, like what effect does it have in the work done? We can say or use the formula that we can also mention the formula, or if you don't want to mention the formula, just write the statement, right? So just say E is equals to, not E just like work done, because they specifically ask work done. So work done is equals to, they're both the same, okay? Don't worry, they're both the same. Don't freak out. So 1 by 2 F delta X, right? This formula. If both F and delta X is greater, then the work done will be greater in order to break this new wire, right? We need a lot of work done to break this new wire than the original wire. That's the only difference, right?